Alright guys, welcome to this page of the notes, and now we're going to get to that second objective, which is using our factoring methods to find the zeros of a polynomial. Remember, when you graph a polynomial, the zeros are going to be where it crosses the x-axis. Now, when the polynomial crosses the x-axis, the value of the function is 0, right? When y is equal to 0, you're crossing the x-axis. So all we have to do is take the polynomial you're given, set it equal to 0, and then use one of the factoring methods or a combination of the factoring methods we've just looked at to factor the polynomial, use the zero product property to split up your factors and solve each of your factors. That will find you the zeros. So let's go ahead and jump right into this and try a few of these. I've given you the polynomial x cubed minus 2x. I've already set it equal to 0. So let's go ahead and go ahead and factor this polynomial and find our zeros, our x-intercepts. I take a quick look at it and quickly recognize that I have a GCF. So let's pull out that GCF, which is an x. I pull out the x, that's going to leave with an x squared minus 2. And that's all equal to 0. Well, now that I have pulled out my GCF, right, the zero product property says that because I have multiplication right here, I can split these guys up and solve each of them individually. So x is equal to 0 and x squared minus 2 is equal to 0. Well, there's nothing else I can do to this one. That just tells me that x equals 0 is one of my x-intercepts, meaning this polynomial will cross the x-axis at y equals 0. At x equals 0, or the origin. This one, I got to do a little bit of work. I'll have to add the 2 to the other side. So x squared is equal to 2. And then to get that x by itself, you just take the square root of both sides. Don't forget to do plus or minus the square root of 2. And since the square root of 2 is not a perfect square, it comes out to be an irrational number, we'll just leave it like that. And please remember, this is two different answers. That's why you need the plus or minus. This actually comes out to be x equals the positive square root of 2 and x equals the negative square root of 2. Those are both zeros as well. And one more quick thing just to sort of refresh your memory. Please notice, what is the degree of this polynomial? Well, it's a two-term polynomial. The degree of the first term is 3. The degree of the second term is 1, which means this polynomial is a third-degree polynomial. Now, if you remember back to a previous section, we said the fundamental theorem of algebra says that the number of zeros for a polynomial is equal to its degree. Well, I have a third-degree polynomial. And how many zeros did we just find? 1, 2, 3. And so again here we're seeing just this another example of where the fundamental theorem of algebra is showing up. Because it's a third degree polynomial, I know I had better find 3 zeros. If I don't wind up with 3 zeros, you made a mistake, something went wrong, go back and figure out what happened. All right, well, now that we just talked about the fundamental theorem of algebra, let's just use that fundamental theorem of algebra right away. I have yet another polynomial. I recognize that it is a third-degree polynomial. So once again, when I get done factoring, I had better have 3 zeros. They could be real, they could be imaginary, or a combination of the two, but I had better have 3 answers. If I don't, something went wrong. So here we go. I take a look at this guy and I recognize, hey, I have a GCF of x. So I'm actually going to pull out a negative x. Pull out a negative x. That's going to leave me with an x squared minus x minus 6. That's all equal to 0. Now, the zero product property would let me split this guy up. However, this is a trinomial, and hopefully you should quickly recognize I can use another one of my factoring methods on this guy. I should be able to factor this as a general trinomial, meaning I can split this guy up into 2 binomials. What I need are two variables that multiply to an x squared, which is the easy bit. That's just going to be an x and an x. And now I need two numbers multiply to a negative 6, sum to a negative 1, which I believe is going to be a minus 3 and a positive 2. Minus 3 plus 2. Let's double check to make sure. Negative 3 times a positive 2. Yep, that's a negative 6. And a negative 3 plus a positive 2 absolutely leaves me with a negative 1. So what we saw here is that I needed to use 2 of my factoring methods to actually factor this guy completely. But now because it's set equal to 0, I have multiplication there and there, which means I can split all these guys up, set them each equal to 0, and solve. Okay, so I get x is equal to 0, x is equal to 3, and x is equal to a negative 2. I apologize, I had to do a little bit of squeezing. Hopefully you can still pretty clearly see there my work. But we said at the beginning, the fundamental theorem of algebra tells me I should have 3 zeros, and that's exactly what I found. X equals 0, x equals 3, x equals negative 2 are going to be my x-intercepts. That's where this polynomial would cross the x-axis, and I get 3 real zeros. Yay, fundamental theorem of algebra. Okay, here we go. Take a look at this one. Once again, I recognize it is a polynomial. The degree of the polynomial is 3. It is a third degree polynomial. So again, I better get 3 zeros when I get done doing this guy. And let's go ahead and take a look at what our factoring method might be. Well, I've got 4 terms. They don't all have a GCF, so I'm going to try group and factor. Since I got 4 terms, more than likely that's going to be what I need. I'll start off by simply grouping the first 2 and the last 2 and see what happens. I can pull an x squared out of that first grouping, so I pull out an x squared, and that's going to leave me with an x minus 1. Out of the next 2 guys, I'm going to pull out a 3. Careful, there's a minus sign in there, so that means I'm going to have a minus 3 right here, not a positive 3, minus 3. And then what that means is, since I pulled the 3 out, 3x divided by 3 is going to leave me with just an x. Oh, wait, I'm sorry, hold up. Let me redraw my parentheses. There we go. So I pulled out a minus 3, right? So a minus 3x divided by a minus 3, right? Negatives cancel, leaves you with a positive x. A positive 3 divided by a negative 3 leaves you with a minus 1. Minus 1. So there we go. I wind up with those guys being the same, which they have to be, right? They need to be the same in order for the method to work. And so I write my GCFs as a quantity, x squared minus 3, and x minus 1 equals 0. Now again, the zero product property is going to let me split those guys up and set them each equal to 0. X minus 1 equals 0, and x squared minus 3 is equal to 0, right? Zero product property lets me split each of those quantities up, and now I solve both of them. X is equal to 1. X squared is equal to 3. Take the square root of both sides. Don't forget your plus or minus. We're taking the square root of 3, which is not a perfect square, so go ahead and leave it as a radical. And also, please recognize it represents 2 answers. I have plus the square root of 3 and minus the square root of 3. And so what I wind up with here is 1, 2, 3 roots, right? X equals 1, x equals plus the square root of 3, and x equals minus the square root of 3 are my 3 roots or x-intercepts. And the fundamental theorem of algebra said I had better get 3. All right, we got another one for you guys here. All right, take a look at this one. And right away I recognize I've got this really large power. Actually, it's a 4th degree polynomial in this case because of that x to the 4th. And this one's actually going to wind up being that quadratic form, right? And I recognize that because I take a look at this guy and I go, hold up a second. I know I can rewrite x to the 4th as an x squared squared. But I was given an x squared. So hopefully, quickly, you can kind of recognize if I rewrite this as an x squared squared minus 6x squared plus 8 I see right away, hey, these guys are the same, and I can do that u substitution where u is equal to x squared. So that's what we do. I now have a u squared minus 6u plus 8 is equal to 0. Now, from here, what I'm hoping is that this is a general trinomial that I can factor into two binomials. Let's check and see. Well, what two things do I need to multiply together to get a u squared? That's the easy bit. It's a u and a u, right? Now, the kind of trickier part, I need two numbers that multiply to a positive 8 and sum to a negative 6. And actually, that's not that tricky. It's going to be a negative 4 and a negative 2, right? Negative 4 times a negative 2 is a positive 8. Negative 4 plus a negative 2 is a negative 6. So there we go. I've got my two factors. We will now set them both, right? Zero product property, because of that multiplication right there. Split them up, set them both equal to 0, and we're going to keep going. Let me slide up just a little bit. There we go. U minus 4 is equal to 0, and u minus 2 is equal to 0. So I get u is equal to 4, and u is equal to 2. Now, here's where that little bit right there is really important, because what happens is my original polynomial was not u equals. My original polynomial was x equals. So I need to put my x's back in. And it's not tricky at all, right? I know that u is equal to x squared. Well, I have a u equals 4, which means x squared is equal to 4. Just substitute those x's back in. Same thing right here, u equals 2, which means x squared is equal to 2. Just put those x's back in. And now solve for x, which is actually really easy. I just need to take the square root of both sides. So x is equal to plus or minus the square root of 4, which of course is 2. So plus or minus square root of 4, plus or minus the square root of 2, plus or minus 2. And there's nothing I can do. That is not a perfect square. And so guys, check out, look and see what happens here. I know, thanks to the fundamental theorem of algebra, this is a 4th degree polynomial, which tells me I should get 4 roots. They could be real, they could be imaginary, or some combination, but I get 4 roots. Well, look how many I got. Plus 2, that's 1. Minus 2, that's 2. Plus the square root of 2, that's 3. Minus the square root of 2, that's 4. 4 roots. I found my zeros for this polynomial by setting it equal to 0 and using that quadratic form factoring method. Guys, thanks so much for joining me for this set of notes. Hopefully that's a good review both of factoring techniques we have already learned in the past and adding a few extra tools to our little bag of tricks here to help us factor some of these polynomials. Thanks for joining me for this set of videos, and I'll see you guys next time.